All right, so yeah, I'm going to talk about how to solve vision without annotating millions of images. By vision, I mean classification of objects. And this is a joint work with Lawrence van der Matten, Alan Jabri, and Nicolas Vaziash that we did at Facebook. So in most of modern computer vision system for object or scene classification, what we usually do is we take millions of images that we annotated at the image level, and then we train a big neural network like AlexNet or whatever. Usually this recipe seems to work very well. You increase or change the architecture and so on, and you get better and better performance. What seems to be something appearing there is that the more data you use, the better the models are. So it seems important to gather as much data as you want. The problem here is that obviously this is not going to scale very well. If you want to learn more and more representation for objects and so on, you are going to have to annotate a lot more images. And also, another problem I will argue for against annotation is that you introduce your own bias when you annotate images. You annotate objects you think are important and so on, and you may miss important concepts. And also, finally, one last thing is that when you use supervised data, you may not take into advantage all the data that are available online, and that's a lot of data. So there have been several approaches that has been proposed recently, or like not in the last 10 years at least, to go around that problem. The first one is usually called web-based supervised learning, which basically consists of basically going online, usually using Google search engine or Bing, and gather data by querying things like headphones or men with headphones. Obviously, the problem with that is that you have a very particular type of images that appears, product images, or in the case of men with headphones, it's basically, I guess, also product images. So, I mean, if you're interested in learning classifier for product, I think that's a pretty good approach. But if you are more interested in basically detecting or classifying headphones in the wild, that might not be the right approach. Also, another problem with that is that when you do your search, you are basically querying Google's or Bing image model, and what you may end up doing is just reproducing their results and reproducing that model. Another approach, very popular currently, is to use unsupervised learning, like with GANs or autoencoder or things like that. They seem very promising. They have like very good early results, and they are they can like scale to tons of. I mean, they can use as many images as you want, and you don't need anything else. The only, I mean, there is a few issues with that. The first one is not very clear that the features you're going to learn are discriminative. The second thing is that you don't really use all the data that are available to you when you get images online. Usually images comes with other information like GPS, hashtags, caption, and so on. So if you go for this type of approach, you're basically throwing away a lot of information that you can get for free. So here what we did instead is to use a new data set that has been released by Flickr like 2 or 3 years ago called Flickr 100 million images. And it's basically images with all of their metadata. So there's like the caption, the title, hashtags, GPS coordinates, user, and so on. In this work in particular, we are just going to focus on hashtags and caption, but I think there's way more to do with this data. So the advantage is that basically with an image, now you have a lot of information that you can use to learn better features. And so that's basically the question we ask ourselves. Can we learn better features with this weakly supervised data? So as I said, there is like around 100 million images with user comments and so on. And what we did is simply to try to predict the words or the hashtags that comes with the image And it can be seen as a multi-label, multi-class problem with noisy labels. And you can use whatever, and we tried different architecture, in particular AlexNet and GoogleNet. So we tried several approaches for to tackle the multi-class, multi-label problems, but what we found, surprisingly, is that actually using a softmax function where you basically consider that each image just comes with one word, you basically pick from your caption one word randomly and just predict that, works actually surprisingly well. It's also very simple to implement and to use and to make it scale. The only thing that seemed to be very, very important was to be careful about how you sample your data. And what we found is that the best solution that was simple to implement was to sample based on class. You basically take all of your vocabulary, randomly pick a word uniformly, and then take an image associated with this word. We tried more sophisticated sampling schemes where you basically kind of do something between the natural distribution of words and the uniform one. That seems to work slightly better, but requires more parameters tuning and so on. So I think that basically using class uniform is the best way to go. And we also, as I said, try different losses, one versus all being one of them. And it works basically as well as softmax. Probably a bit better if you calibrate well your threshold at the end, but it's not significantly better. So one trick is that when you work on this type of data, you have a lot of classes. So we went up to 10,000 words in this, 100 words in this, 100,000 words, sorry, in this work. But then now we are more at around 1 million. And when you do that, you cannot just run a full softmax directly. So that's a problem, and there has been a lot of work to deal with that, especially in language modeling and NLP. Some of them are like hierarchical softmax, or I think a work presented earlier here from Edouard Grave called adaptive softmax and so on. But here we also try to use something very simple, and we basically use important sampling. So the idea is very stupid. You just sample a few negatives each time, and you just normalize over them. So we basically sample, I think, around 1,000 per example, and that's it. So you can prove a bound on it. I don't know if it's very useful, but you can basically show that if you do this technique of important sampling, you somehow optimize something related to the original bound, which is a good news. Our bound is completely not tight at all and really weak, but at least it was confirming that we aren't doing something completely stupid. So to train at scale, there is a few tricks to use. Basically, doing some of the work on images on the CPU side, using multiple GPUs asynchronously if you can, and basically, even with all that and all the trick I described before, it still takes several weeks to train this type of model. So here is now like the results we obtain with this type of thing. So if you use, we compare basically our model end-to-end train on this data and model that has been trained before on ImageNet, and then you just learn the head, so just the classifier. And if you, usually that's what people do when they try to their model on a new problem. If you do that, you see that basically you get a significant boost by training it end-to-end on the same distribution as the one you've been working on. So that's a good sign. I mean, it's kind of obvious because basically you are fine-tuning on the same data, but this is pretty good. Then now you can ask yourself, how much data do you need, basically? I mean, how does that scale with data? So here we basically look at the score for prediction. if you increase the number of images you use for training. So basically, it's not very surprising, but as you increase the training set, you get better and better performance. What is a little bit surprising is that, so that's with AlexNet, but we observe the same thing with GoogleNet, is that it starts to plateau after a certain number of images. And it's not very clear why, if it's a capacity problem or if it's because the dictionary was too small and you have to really go to bigger output space to get improvement, but so far we've always seen this plateau effect. Here's examples of what you can do when you train model on that scales and on this data. You can have classifier for a lot of concepts that are probably not in ImageNet or a lot of computer vision data, like vintage, abandoned, art, things like that. You can also easily do image retrieval. That's all images from Yahoo. So then you can start playing around with this type of images. You can do it with arts as well, people playing guitars, and so on. We also looked a little bit of what happens when you look at the images and how they cluster based on their visual features, and a lot of not surprisingly, images are being clustered by different type of classes. Like you can see that here there is animals, different type of animals, black and white images. That's not very interesting. Here is the sports cluster that we observed. You have basically the indoor on one side, then the outdoor sports, and if you look closely to them, you will actually see that they have kind of a hierarchy of classes that appears naturally just by looking at the dot product between the embeddings. And that wasn't fed to the model. You can also look at the words embedding, which is basically looking at the classifiers and just normalizing them and do cosine. And as well, you also see clusters appearing, like names here. Where you have on one side female name and male name. You also have here, I think, a cluster of words related to music, and they are in multiple languages because this is on Flickr. It's not only English-speaking people; it's any language. So you have all that coming together. Then to evaluate a little more the quality of the feature we learn, we tried different transfer learning problems to specific domains like scenes, action, fine-grained classification, and sport. And what we observed is that basically if we train on Flickr, compared to if we train on ImageNet, we obtain the same performance if you have an AlexNet, slightly better, but in the same ballpoint, but for fine-grained, which is not very surprising. But we have a drop of performance if we use GoogleNet. Or at least what we observe is that GoogleNet trained on ImageNet get a boost compared to AlexNet, while both AlexNet or GoogleNet kind of get the same type of performance. So that was a surprising finding. We are not completely sure why we observed that. Is it that GoogleNet was really tailored for ImageNet, or is it that we didn't tune well or the parameters to learn it on Flickr? We are still investigating that, but it was a surprising finding though. The same for, we also tried transfer on Pascal VOC, and we basically observed the same thing. For AlexNet, we are actually starting to get better than the one trained on ImageNet, but we also observe that this is less the case when we go to GoogleNet. When we combine both, well, we get improvement from the two models. We can also use a lot of tricks and so on to get to a 82 min AP, which was at the time we ran this experiment close to state of the art. I'm not sure if it was, but at least very close. Again, if we look at how many images you need to basically get a model that has the same level as the one trained on ImageNet. We observed that, so now we have a slightly better algorithm for training, so now we get actually better performance, but overall I think the point that is interesting is the one where we start crossing, if we ever cross it, the ImageNet line, and that's basically a factor of 10. So you need between 10 and 20 million images with no annotation to start getting the same performance as the one you get with 1 million images from ImageNet. We also evaluated the quality of our embeddings, of our word embeddings compared to Word2Vec. So not surprisingly, I think the most interesting is when you start to go to a relatively big dictionary. Not surprisingly, our model is worse than Word2Vec, but that's normal. We have been only trained on 100 million captions, while Word2Vec has been trained on, I don't know how many billion of words, but way more than what we got. So it's not very surprising. When we combine both, we got a small boost over Word2Vec, which is good, I guess. We also looked at if we could use this model to do a bit of translation. Of course, that's not the way you should do translation, but since all the words embedding and their similarity has been trained through a visual feature, it's a natural, I mean, it is, I think, a good metric to see if it's able to capture good visual representation, because you have same words in French and English to describe the same type of objects, and we basically get relatively good scores, like not top 1, but top 5. So it's like examples of what we can learn: infrared, tomatoes, like libraries, like the 10 top cosine products. So it's mostly the concepts that are visually significant. So we have, since, so this paper was at ECCV, and then we have extend on that work. And the natural way of extending it is that instead of printing words, you start printing n-grams, which is what we did. The motivation behind that is, like, if you see this image of, I don't know exactly what it is, it's like a car, I don't know. But if you just go for unigram, you will have burning, which is kind of accurate because there's flames. But if you go to bigram, obviously you can capture things like Burning Man, which I think is where this thing happened. So you have obviously information that if you just predict words, won't be enough. So we extended that to n-grams models, and that also allows us to do things like language model and zero-shot learning, because now you can basically predict any kind of words or trigrams, fourgrams, and so on. And so any kind of classes you usually have in normal computer vision datasets. And so what we observed is that for the task of caption retrieval or image retrieval, our model, which is purely based on n-grams prediction, gets performance which are often surpassing the one based on RNNs and all these type of models, and gets okay score compared to the one which has been designed for this task. And this our model, like these guys, has been trained on Flickr, and then we just fine-tune the head on the Coco Flickr and so on. So it's really trained on 100 million, and then we just do transfer. So that's, I think, kind of promising that with a simple model and trained with no annotation, you can get performance which are comparable. It also allows to do, well, zero-shot learning and some cool visualization. Like you can basically see like query for each for n-grams and where it appears in an image and so on. So that's kind of nice. So in conclusion, we have in this works we have shown that you can actually get relatively good vision models without any annotation. It is not yet completely beating the one trained on ImageNet, but I think it opened the doors to like basically trying to get away from purely annotated data set to the one that basically you get online and just train from there. And the big advantage you get by doing that is that you can learn concepts that probably you wouldn't thought of annotating. And if there is new concept appearing, then you can basically get them. So that's it. Thank you.
Questions?
Thanks. I got the impression you said that you found that GoogleNet is like the architecture is over-specific or overfitting to ImageNet, like not the weights, but the architecture is overfit.
Yeah, I mean that's one explanation. I don't.
Yeah. Do you have experiences like like Inception v3 or like the Inception v4? If it has the same
no, so we tried also since then ResNet. ResNet works. I mean the gap is bigger when it's when you train on Flickr than what we observed with GoogleNet. But it's also not as good as when the gap in performance on transfer learning is not as big as what you get from ImageNet. So if you take an AlexNet and a ResNet train on ImageNet, you get I guess a gap of like an improvement of 20% on transfer learning, and we only get 10%. We will still get improvement. With the GoogleNet, we didn't, but we still observe the same effects a bit with the ResNet, which also suggests that there might be more than just like the architecture not being good enough. I mean, too tailored for ImageNet.
Other questions?
Yeah.
So in the beginning, you motivated that you avoid or you would have a bias if you annotate yourself. Mm. So now you replace the bias of the annotator by the Flickr users, which
yes.
is also a pretty homogeneous crowd, right? So is there any way to break out of even that?
That's a great question. Obviously, yeah, we also have a bias, but the good thing is that we don't introduce it ourselves. It's all. I mean, I always prefer if I work on someone else's bias than mine. I don't think there's really a way to like remove any type of bias. Whatever you do, you're gonna get one. Like if you put like a camera on a robot and you just take pictures randomly, you will still have bias probably because you cannot travel all over the world and so on. So you will have one, but at least here it's I don't like I don't control it, and hopefully like so Flickr is a particular beast, but that's basically the only one which has public data available. But I guess with other social media, you may also have like more images and maybe then less bias. I don't know, or at least I don't know, more information coming from all that. But yeah, you will always have a bias, that's for sure.
Other questions? I have one. You said that you flattened the distribution when you trained by just using uniform over the words or the tags. Is that because in the end, you are using it in a setting where your test set or...
No, so the test set was not uniform.
It was ZIF.
Yeah, it was a ZIF distribution. Okay. It's just that the head of your distribution contains a lot of not so interesting words.
Well, it's ZIF on a different distribution.
No, so it's a ZIF, so it's the same ZIF distribution of words that we tested on. I think the reason why it was important to make it uniform, and I don't think it's like, again, I don't think it's the best distribution necessary to use. I think there's like works to be done here. Is that in the head of the distribution, there's a lot of words which are not like visually very interesting. And the visually interesting one, like for example, the word park, I guess people take a lot of photos of parks, was like 2 or 3 times bigger than the second one, which was I think city or something like that, are visual concepts that are really easy to learn. So if you just look at them all the time, then you get the perfect park classifier, but that's it. So I think, I mean, it's kind of natural because there is a lot of visual concept that appears later in the distribution. by doing it uniformly, we obviously pay a price of like overfitting on the tail, which is like a bad idea. But again, when with 100K words on 100 million images, we don't actually, we kind of cut off the tail, so we cheated a little bit here. Like we don't have really the tail. I think this problem will appear more when you go to like 1 million classes.
Okay, let's thank the speaker again. And,